We're living in a moment where AI feels like it's just everywhere, constantly evolving.
Mhm.
But have you ever stopped to think about what actually powers all that intelligence?
That's a great question.
It's not just magic, right? It's this whole intricate world of infrastructure.
Yeah, a whole foundation.
And getting a handle on that infrastructure,
Yeah.
that's becoming, well, pretty crucial for anyone trying to really understand our tech-driven future.
Absolutely. The dazzling AI apps get the headlines, but without the right foundations, the specialized hardware, the smart software, how it's all architected, those breakthroughs just wouldn't happen.
Right.
It's like marveling at a Formula One car without thinking about the engine and the chassis, the
Oh.
serious engineering underneath.
Exactly. So for this deep dive, we've got something maybe a little different, but trust me, it's packed with valuable insights.
Uh-huh.
We're going to unpack the NCA-AIIO exam.
Okay.
Now, I know what you might be thinking. An exam? Really?
Yeah.
But this exam is laser focused on the very infrastructure we're talking about. And honestly, even if you're not planning to ever take it, the topics it covers, they're essential for understanding what's really going on under the hood of modern AI.
Think of it as a kind of curated overview. It hits the core technologies and concepts that make today's AI actually run.
Mm-hmm.
The exam uses multiple choice questions, to test knowledge across this infrastructure.
You're right.
And our goal today is to explore some of those questions, figure out the right answers, and maybe most importantly, understand why those are the right answers.
Yeah, the why is key.
Consider it maybe a rapid way to gain some really solid, valuable knowledge.
Couldn't have put it better.
Yeah.
And yeah, we're not here to quiz anyone, promise.
No tests today.
We're just going to walk through some sample questions, reveal the correct answer, and then crucially, dig into the ideas behind them. We're aiming for that practical understanding, the kind of knowledge that actually sticks.
Sounds good.
All right, let's dive into our first area then. It's all about something called NVIDIA Tensor Cores. What makes them so special?
Well, what's interesting here is that tensor cores are a perfect example of how specialized hardware has just, revolutionized AI.
Okay, so here's the question. What is the primary benefit of using NVIDIA Tensor Cores in AI workloads? Your options are A, accelerated matrix operations for deep learning tasks, B, increased CPU memory bandwidth, C, support for hard drive caching, or D, enhanced cooling for AI servers.
Okay, and the answer, according to the exam prep, is A, accelerated matrix operations for deep learning tasks.
Matrix operations. Okay, that sounds a bit like high-level math class. What are we actually talking about here when it comes to, training AI?
Yeah, it can sound intimidating.
Very.
But imagine you have just a massive spreadsheet, tons and tons of numbers, right?
Okay.
And you need to do basically the same calculations across loads of rows and columns all at once.
Okay, like parallel calculations.
Exactly. That's kind of a simplified way to think about matrix operations in deep learning. These models involve a huge number of those calculations, especially multiplications. It's fundamental to how they learn patterns from data and, make predictions.
So tensor cores are chips or parts of chips specifically built to handle these massive spreadsheet-like calculations much, much faster than a regular computer chip could.
Precisely. They are specialized units within NVIDIA GPUs, designed specifically to be incredibly efficient at these large-scale tensor computations.
Tensors.
Yeah, think of tensors as just more complex versions of those spreadsheets, maybe with more dimensions.
Got it.
By taking on and speeding up these core operations, tensor cores dramatically improve the performance of AI tasks.
So how much faster are we talking?
Well, think of it this way. Before tensor cores, training a complex image recognition model might have taken weeks. Weeks.
Wow.
Now, thanks to this kind of specialized acceleration, it can potentially be done in hours or sometimes even minutes. It just fundamentally changes the speed of AI research and development.
That really puts it into perspective. Okay, question 2. This takes us to the stage after the AI has learned its stuff. The question is, in the context of AI model deployment, what is the role of NVIDIA Triton Inference Server? Choices. A, packaging data into training sets. B, simplifying and optimizing AI inference across multiple frameworks. C, designing custom neural networks. Or D, encrypting AI model weights.
Okay, and the correct answer here is B, simplifying and optimizing AI inference across multiple frameworks.
Okay, so our AI model is trained, it's smart. What does it actually mean to deploy it, put it to work?
Yeah, deployment is essentially taking that trained intelligence and making it accessible, making it usable in real-world applications.
Okay.
Think of it like a chef who's perfected a new dish, right?
Huh.
Deployment is about getting that dish onto the restaurant menu so customers can actually order it and enjoy it.
Makes sense. And that's where Triton Inference Server comes in.
Exactly. Now, the world of AI isn't, one size fits all. There are different underlying technologies, different recipes, if you stick with the analogy,
Right.
for building AI models.
Mhm.
Things like TensorFlow, PyTorch, ONNX. You hear these names.
Hmm.
What's fascinating is that Triton acts like a universal translator and server combined. It's capable of handling models built with all these different approaches.
Ah.
So it really simplifies the process of putting those models into action. Instead of needing separate kitchens for each type of cuisine, Triton manages them all in one efficient space.
So instead of having to set up completely different systems for each type of AI model, Triton can just handle them all. That sounds like it could save a lot of headaches.
It absolutely does. Huge
Oh.
headaches. And it's not just about making things simpler. It also makes them run better.
Yeah.
How so? Well, Triton has built-in features that optimize how these AI models are actually used when people make requests. We call that inference. Things like managing different versions of a model or handling lots of requests at the same time really efficiently. So this ability to work with different frameworks and boost performance, that's Triton's core job. It helps avoid that feeling of being totally overwhelmed by a chaotic mix of AI technologies.
Right, help streamline things. Okay, let's tackle question 3. This one brings us closer to where the data is actually being generated. The question: which characteristic best describes edge computing in AI infrastructure? Options: A, training models in the cloud before deploying to devices. B, running GPUs in centralized data centers. C, processing data locally to reduce latency and bandwidth use. Or D, using cloud-based CPUs for low-power applications.
The correct answer there is C, processing data locally to reduce latency and bandwidth use.
Edge computing, we hear this term quite a bit. What does it really mean, in the context of AI?
Okay, imagine you have, say, a security camera constantly recording video.
Mm-hmm.
Instead of sending all that video data way off to a data center in the cloud for analysis, edge computing means you put the AI processing power right there with the camera, or at least very nearby.
Oh, okay.
It brings the intelligence closer to the edge of the network, right where the data starts.
So the AI analysis happens right on the device itself, or maybe a little server in the same building.
Precisely. And the big advantages are speed, we call that reduced latency, right? The time it takes for a response.
Yeah, less delay.
And saving on internet costs, which is the bandwidth part. You're not constantly uploading these massive amounts of data to the cloud.
Right.
Think of it like having a local expert right there on hand instead of always having to call a consultant across the country. Much faster, often cheaper.
That makes a lot of sense, especially in situations where, a quick reaction is critical. Can you give us another quick example where edge computing would be really important?
Oh, sure. Consider a smart factory. You've got robots working on an assembly line.
Okay.
If a robot's camera detects a defect in a part, it needs to react instantly, right? To maybe stop the line or reject the part.
Yeah, immediately.
Sending that image data all the way to the cloud and waiting for instructions, that would be way too slow. Edge computing lets the robot or a local system make that decision and take action right away. Low latency is key.
Okay, yeah, that paints a really clear picture. Now, question 4 is a bit different. It's a two-part question. It asks, when setting up a multi-tenant AI infrastructure, which 2 strategies help ensure fair and efficient GPU resource utilization?
The multi-tenant challenge.
Right. Options are: A, use first-in, first-out scheduling for GPU access. B, set GPU quotas per user or workload. C, limit network bandwidth for training jobs.
Yeah.
D, use multi-instance GPU MIG to divide GPU resources. And E, prioritize long-running tasks only.
Okay, so you need 2 here. And the 2 correct answers are B, set GPU quotas per user or workload, ADD. Use multi-instance GPU, MIG, to divide GPU resources.
Multi-tenant. So that means we've got multiple different users or maybe different projects all sharing the same underlying AI hardware, especially those powerful, expensive GPUs.
Exactly that. And when you have shared resources like that, yeah, you need ways to make sure everyone gets a fair slice of the pie, so to speak.
Right.
And also that the valuable resources are used effectively, not just, hogged by one user or one big job.
Okay, so let's start with B, setting GPU quotas. That sounds pretty straightforward, like saying, okay, you get this much GPU power and that's your limit.
That's the basic idea, yes.
Yeah.
By setting defined limits, maybe on processing time or memory usage per user or project, You prevent a single, really intensive task from just taking over all the GPU resources and slowing everyone else down to a crawl.
Makes sense.
It helps ensure a sort of baseline level of performance for all the different tenants using the infrastructure.
And the other correct answer was D, using multi-instance GPU or MIG. What's the magic behind that? Sounds
It
fancy.
is pretty clever, actually.
Hmm.
MIG is a technology built into some of the newer, more powerful NVIDIA GPUs. It allows a single physical GPU to be securely partitioned or divided into several smaller, completely isolated virtual GPUs.
Ah, like slicing up the hardware itself.
Kind of. Think of it like taking that whole pie, the physical GPU, and carefully slicing it into individual, self-contained slices. Each slice, or MIG instance, gets its own dedicated processing engines, its own memory, its own bandwidth.
So they don't interfere with each other.
Exactly. The workloads running on different MIG instances are totally isolated. This not only improves how efficiently the overall GPU can be used, maybe running several smaller jobs perfectly fits better than one huge one, but it also really enhances fairness by guaranteeing a certain level of resources to each user or application assigned to an instance.
That makes perfect sense. So quotas for overall limits and MIG for actually carving up the GPU. Two key tools for keeping a shared AI environment running smoothly and fairly.
Precisely.
Okay, let's move on. Question 5 brings up NVIDIA's NGC. The question is, which feature of NVIDIA NGC supports reproducibility and consistency across AI experiments? Options are A, custom fan curve profiles, B, pre-built and optimized containers for deep learning frameworks, C, proprietary GPU firmware updates, D, user-defined network latency configurations.
Okay, for NGC and reproducibility, the answer is B. Pre-built and optimized containers for deep learning frameworks.
We've mentioned containers a couple of times now. Can you give us maybe a quick refresher on what they are in this software context?
Sure. Imagine you're trying to ship a really delicate piece of equipment, right?
Okay.
You wouldn't just toss it in the back of a truck. You'd carefully pack it in a special container, probably with padding, all the bits it needs, so it arrives safely and in perfect working order.
Right.
A software container is kind of similar. It bundles up an application like an AI model or a training script, along with everything it needs to run. That means the code itself, all the necessary software libraries it depends on, system tools, configuration files, everything.
All packed together.
All packed together in one neat, isolated package. And the key thing is, this means the application will run the same way no matter where you deploy that container.
Ah, consistency. Okay, so how does NVIDIA NGC fit in here?
So NVIDIA NGC is basically a hub, like a big library or registry, for AI and data science resources provided by NVIDIA. One of its absolute key offerings is a curated collection of these software containers.
Gotcha.
And these aren't just any containers. They're specifically built and optimized by NVIDIA for running popular deep learning tools like TensorFlow, PyTorch, you name it, on their GPUs. They're tested to ensure they deliver top performance.
Okay, and how does using these pre-built NGC containers help with making AI experiments reproducible? That was the question.
Well, think about it. If everyone working on a research project, or even just you trying to rerun your own experiment later, starts with the exact same NGC container, they're all using the exact same software environment, down to the specific versions of every library.
Right, eliminates variables.
Exactly. It eliminates a huge potential source of problems and inconsistencies that can pop up when different people have slightly different software versions installed on their machines. It's classic works on my machine syndrome avoidance.
Yeah.
So if your AI experiment runs correctly inside a specific NGC container, you can be much more confident that someone else using that exact same container, maybe months later, will get the same results,
Okay.
which leads to more reliable, more trustworthy research and development. It's like having a standardized, guaranteed recipe for the software part.
That makes total sense, like a standardized science lab, but in software form. Okay, question 6 is about keeping the lights on, basically. You need to ensure high availability of GPU-accelerated workloads in your AI data center. Which strategy is most suitable? Options. A, deploy workloads across multiple redundant nodes with failover systems. B, run all jobs on a single, really powerful GPU server with extra memory. C, use low-power CPUs to balance thermal loads. D, limit the number of GPUs per server to reduce complexity.
Right, high availability is crucial. The best answer here is A, deploy workloads across multiple redundant nodes with failover systems.
High availability. What does that practically mean for an AI system that's being used, in the real world? For a business, maybe.
It means making sure that your AI applications and services are essentially always up and running, with minimal interruptions or downtime.
Okay.
Think about critical online services you rely on, like your online banking or maybe e-commerce sites. You expect them to be available whenever you need them, 24/7, ideally.
Yeah, you get annoyed if they're down.
Exactly.
Yeah.
High availability aims for that same level of reliability for important AI workloads, which might be doing anything from customer service chatbots to critical medical image analysis. Downtime can be costly or even dangerous.
Got it. So why is spreading the work across multiple redundant nodes the best approach for achieving that?
Well, the key word there is redundant. It means having backups, duplicates. By running your AI tasks on several independent servers, those are the nodes you create resilience.
Ah, so if one fails.
Exactly. If one server has a hardware problem or needs maintenance or just fails unexpectedly, the other identical servers can immediately take over the workload.
And the failover systems part.
That's the automated mechanism that makes the switch happen. These systems constantly monitor the health of the servers. If they detect a failure on one node, they automatically, and hopefully seamlessly, redirect the incoming work or the ongoing tasks to one of the healthy, redundant nodes.
So it's like having a backup generator for your house that kicks in automatically when the main power goes out. You might not even notice the switch.
That's a great analogy, yes.
Yeah.
If one part of the system stops working, another identical part immediately steps in to keep things running smoothly. The other options listed just don't provide that crucial safety net of automatic backup and recovery. A single powerful server, option B, is a single point of failure.
Right. Makes sense. Okay, question 7 gets to the absolute core of NVIDIA's acceleration technology. Which of the following most accurately describes the role of CUDA in AI infrastructure? Options. A, a library for managing virtual machines. B, an API and programming model enabling parallel computing on NVIDIA GPUs. C, a benchmarking tool for deep learning model accuracy. D, a data versioning system.
Okay, CUDA. This one is fundamental. The correct answer is B, an API and programming model enabling parallel computing on NVIDIA GPUs.
CUDA is another one of those terms that comes up constantly when we talk about NVIDIA GPUs and AI. How would you explain it simply? Like, what is it?
Okay, think of your computer's main processor, the CPU, as like a very smart, very fast manager that's good at handling tasks one after another, or maybe a few complex things at once.
All right.
An NVIDIA GPU, on the other hand, is more like having an army of thousands of smaller workers who are really good at doing lots and lots of simple calculations simultaneously, in parallel.
Okay, massive parallelism.
Yes. Now, CUDA is essentially the language and the set of tools that allow software developers to talk directly to that army of workers on the GPU.
Ah, the communication layer.
Exactly. It provides an API and application programming interface, which is just a standardized way for software to give instructions. CUDA lets programmers write code that can harness that massive parallel processing power of the GPU for general-purpose computing tasks, not just for drawing graphics on your screen.
So it's the key that unlocks the GPU's power for things like the complex math needed in AI.
Precisely. CUDA allows AI frameworks and applications to tap into the thousands of processing cores inside an NVIDIA GPU and run those matrix multiplications and other calculations incredibly fast all at the same time.
So without CDA, it would be much, much harder for AI software to really get the speed benefits from NVIDIA GPUs.
Oh, absolutely. CUDA is foundational. It's the bedrock technology that enables the GPU acceleration that has driven so much progress in AI over the last decade or more. Most major AI frameworks are built on top of it.
Gotcha. Okay, question 8 looks at the challenges that come when you try to make things even bigger and faster. What is a key challenge when scaling AI training workloads across multiple GPUs? Options. A, the need for faster hard drives. B, synchronization overhead and inter-GPU communication. C, incompatibility of TensorFlow with parallel tasks. D, insufficient RAM on the CPU side.
Scaling challenges, right. The correct answer here is B, synchronization overhead and inter-GPU communication.
Okay, so we know that using more GPUs, maybe 8 or 16 or even hundreds in a cluster, can significantly speed up the huge task of training large AI models.
Ideally, yes.
But it's not always a simple case of more GPUs equals proportionally faster training, is it?
That's exactly right. It gets more complicated. When you distribute your training job across multiple GPUs, each GPU typically works on a different chunk of the training data.
Okay.
And each one calculates updates to the AI model based on what it sees in its data. But for the overall model to learn correctly, All those individual updates from all the different GPUs need to be shared, combined, and synchronized regularly.
They all need to agree on the changes.
Yeah, they need to stay on the same page effectively. And that sharing and combining, that's where things can get tricky, especially as you add more and more GPUs.
How so?
Well, this communication between the GPUs sending updates back and forth, maybe across a network like NVLink or InfiniBand, takes time. It consumes communication bandwidth.
Right.
As you scale up to many GPUs, the amount of communication required increases significantly. If this inter-GPU communication isn't managed very, very efficiently by the hardware and the software, the time spent just waiting for data to be shared and synchronize the overhead can actually start to eat into the time saved by having more processing power. It can become a bottleneck.
So you reach a point of diminishing returns.
Exactly. You might double the GPUs, but get much less than double the speed up because they spend so much time talking to each other. Developing communication libraries and network architectures to minimize this overhead is a huge area of ongoing work in high-performance computing and AI infrastructure.
Okay, that gives us a really interesting peek into some of the more advanced challenges in building large-scale AI systems. Now, question 9 is about something maybe more mundane, but still critical: keeping our valuable hardware healthy. Why is it important to monitor GPU temperature and power usage in AI infrastructure? Options: A, to reduce memory leaks in software; B, to comply with data privacy laws; C, to prevent overheating and maintain long-term performance; D, to track user login patterns.
This one should be fairly intuitive, I think. The correct answer is C, to prevent overheating and maintain long-term performance.
Yeah, seems straightforward. But why is it particularly critical for GPUs when they're running these heavy AI workloads?
Well, as we've discussed, AI workloads, especially training deep learning models, are incredibly demanding computationally. They push the GPUs really hard.
Right.
This intense processing generates a significant amount of heat, way more than just browsing the web or running office software. And these high-end GPUs are also designed to draw a considerable amount of electrical power to fuel all that computation.
Okay, so what are the potential downsides if you just let them run hot without keeping an eye on things?
If a GPU gets too hot, beyond its safe operating limits, it will usually automatically protect itself through something called thermal throttling.
Throttling.
Yeah, it deliberately slows down its processing speed to reduce heat generation and prevent damage.
Ah, so your performance drops.
Exactly. Your AI tasks start running slower, maybe significantly slower, defeating the purpose of using the powerful GPU in the first place. And even worse, if GPUs are allowed to run too hot for extended periods, it can actually cause permanent physical damage to the chip, drastically shortening its lifespan.
Ouch, these things aren't cheap.
Not at all. So monitoring temperature is crucial for preventing damage. And monitoring power usage is also important, partly to make sure you're not overloading the power supplies in the server or the data center rack, but also just to understand the operational costs. These things can consume a lot of electricity.
So it's really about both ensuring consistent performance right now and protecting your very expensive hardware investment for the future. Makes sense. All right, last question, number 10. This brings us back to consistency again. Which best practice improves model portability and consistency across different development environments? Options: A, avoiding any external software dependencies; B, using containerized environments with standardized configurations; C, building models on multiple operating systems manually; D, disabling GPU acceleration for compatibility.
Okay, for portability and consistency across environments, the answer is B again. Using containerized environments with standardized configurations.
Right, containers again. We talked about them with NGC providing pre-built ones. How do they generally help with this idea of portability, taking an AI model and running it smoothly in different places?
Well, just as we discussed with NGC, the fundamental benefit of containers is that they package together everything an AI model needs to run the model code itself. All the specific versions of libraries it relies on, maybe system tools, configuration files, everything, into that single self-contained unit.
The whole environment in a box.
Exactly. Which means that no matter where you move that container, say from your data scientist development laptop to a shared testing server, to the final production environment maybe running in the cloud, it carries its entire software environment with it. It will find the exact same libraries, the same versions, the same setup inside the container, regardless of the underlying host operating system or hardware differences. Within reason, of course.
So you completely sidestep that classic frustrating situation where something works perfectly on your computer, but then it breaks completely when someone else tries to run it or when you deploy it.
Precisely. By using containers with standardized, well-defined configurations, you ensure that your AI model behaves predictably and consistently across all the different stages of its lifecycle, from initial development and experimentation right through to deployment and operation.
Nice.
This massively improves portability. It makes it so much easier to move and run your models without encountering those unexpected, time-wasting issues caused by subtle differences in the underlying software stack.
And just quickly, why not the others, like A, avoiding dependencies?
Option A, avoiding any external dependencies, is usually just unrealistic for complex AI projects. They almost always rely on multiple libraries and frameworks.
Right.
Option C, manually building and testing on every single target OS. That would be incredibly time-consuming, error-prone, and hard to maintain.
It's a nightmare.
And option D, disabling GPU acceleration. Well, that would completely negate the performance benefits we've been talking about this whole time. It defeats the purpose for most serious AI work. So containers really are the standard best practice here.
Well, we hope this deep dive has not only informed you, but maybe also sparked your curiosity to learn more about some of these areas.
Yeah, hopefully it wasn't too dry.
If any of these topics, Edge, MIG, Triton, whatever particularly caught your interest, we definitely encourage you to explore them further. This conversation is really just the starting point in a vast and constantly changing landscape.